Okay, so we've been talking about probability stuff, so we're going to continue that conversation with looking at specific things called independent and dependent events. And in reality, these two things are very similar when we talk about independent and dependent. The only difference is that one thing is the probability doesn't change with independent events, but when you have dependent events, it does. Okay, so let's take an example first to talk just to define them a little bit. Independent events would be like if you have a deck of cards and you shuffle them up and somebody takes a card from you, okay? Then you put it back in the deck, shuffle them again, and take out another card. So since the number of cards I've got in my deck for both of those is the same, it would be independent because the probabilities don't change, right? Like you're trying to draw a queen out, okay? So the probability of getting a queen would be 4 out of 52. All right, so I draw a card out. Hey, it's a queen. Great, 4 out of 52. And then I'm going to draw another card out. Well, now when I go to draw the other card out, okay, I shuffle the deck again, put that one back in. So if I've replaced it, then we have independent events. If I take it out and set it down on the table, I now only have 51 cards, and so that's going to be dependent events. But when you do the probabilities, though, you're still the main thing is that you're going to be multiplying them together. Okay, we rarely do any adding when it comes to probabilities. So independent events are where the occurrence of one event does not affect the probability of another one. Okay, so when I flip a coin, what's the probability I get ahead when I flip a coin? Okay, 1/2, right? 50% or 1/2, right? So if I take that same coin and flip it again, has the probability changed? No, it's the same. And so those are independent events because the probability is all the same. Take a die. Okay, I roll the die, right? The probability of getting a 5 is what? 1/6. So I pick up that die again, roll it again. Does the probability of getting a 5 change? No, it's still the same, right? Some people think if I hold it just like this or hold it like this or make sure the 6 is up or the 5 is up or whatever, that you'll get what you want, okay? Well, if you're a perfect roller and you do it the same way every time, you might be able to figure that out. But so all this says here, the probability of independent events, if A and B are independent, then the probability of A and B happening, we're just going to multiply those probabilities together. Okay? So A and B are going to happen, so we're just going to multiply those probabilities together. So here we have this specific six-sided cube labeled with the numbers 1, 2, 2, 3, 3, and 3. 4 sides are red, 1 side is white, and 1 side is yellow. And they want us to find the probability of tossing a 2 and then tossing the 2 again. Okay. So from this information, what's the probability that I toss this number cube and I get a 2? Okay, 2 out of 6. So the first toss, I get 2 out of 6, which is 1/3, right? So then I take that same cube and I roll it again. What's the probability I get a 2 again? 1/3. And so then I'm just going to multiply those probabilities together. So the probability of rolling a 2 and then rolling a 2 again would be 1/3 times 1/3. Because each time the probability of the second event is not affected by the first one. Okay. Right. Says, how about tossing a red? This thing likes me in the morning. Okay. So tossing a red, then a white, then a yellow. Okay. What's the probability I get a red? What is it? 4/6 for a red. Okay. All right. So we have 4/6 or, wow, please just go away. So the probability of getting a red is 4/6, and the probability of a white 1/6, and then yellow. So then we're just going to multiply those numbers together. So we would get 4 over 216. And then we want to always simplify these fractions. Okay, so do these two. Now, when you have dependent events, we're still going to be multiplying. It's just that what happens first affects what happens second. So, for instance, if we were working with, drawing stuff out of a bag or something like that, if we put it down, okay, so that we change the probability, then it becomes dependent. So here we have, there's 3 pieces of fruit in a bag, 2 lemons and a lime, okay? And here's what happens given the situation. So first of all, since there's 2 lemons and 1 lime, there's a 2/3 chance that the first one I pull out is a lemon, a 1/3 chance that it's a lime. Well, if I take that piece of fruit and I set it down to the side and don't put it back in the bag, I've now changed the probability. If the first one was a lemon and I set it down, I now have a 1/2 chance of getting a lemon and 1/2 chance of a lime because there's one of each in there. If the first one I pulled out is the lime, then now I have a 100% chance of getting a lemon and 0% chance of getting a lime. So you have to pay attention to what happens first. So it says to find the probability of dependent events, you can use what's called conditional probability. And this is read the probability of event B given that A has already occurred. Okay? In other words, if the first one was a lemon, I pulled it out, that's already happened. Now I'm just focusing on what's left then. So if A and B are independent events, then the probability of B and A equals the probability of A times the probability of B given that A has already happened. So it really is not as complicated as it sounds, but some of that sounds a little complicated. So 2 number cubes are rolled, 1 white and 1 yellow. Explain why the events are dependent, and then find the indicated probability. So when we show that they're dependent, then we need to show that these 2 probabilities are not the same, okay? That they're not equal. So we need to pull out our number cube once again. Even though we use red and blue, we can still work with them. So says, first of all, it says the sum is greater than 9 and the white cube shows a 6. So first of all, we want to find the probability that the sum is greater than 9. How many of those combinations have a sum greater than 9? How many? 4 out of the 36? Greater than 9. So 10, 10, 10, 11, 11, and 12. So there's actually how many? Okay. 6 out of the 36 show a sum greater than 9. Now, and I always forget that this is written backwards. Now, in this case, it says, what's the probability that the white die has a 6 or shows a 6 given that the sum is greater than 9? And so what happens there is all I care about right now then is these 6 combinations, because it says, first of all, I have to have a sum greater than 9, and then how many of them show the white one with a 6? Well, you could say red or blue, but either way, how many of them? Okay, 3 of them do. So then my answer here is 3 over 6, which is 1/2. And since these two things are not equal, that means they're dependent. Okay? Because those two things are not equal, that's why they're dependent. And my answer to this problem is then the product of those two numbers, which would be 1/6 times 1/2, which is 1/12. Out of the 6 that have a sum greater than 9, 3 of the white ones show a 6. Okay, or 3 of the red ones if you want. Okay. So then my total amount that I've got is I have 3 out of all of them meet that criteria, which is 1/12. Hello? Yeah? Yeah? Okay. They requested to have it done too, huh? Never mind. Okay, 128. Okay, bye. Jocelyn and Mackenzie, you guys need to go to room 128. Get to get your eyes checked. All right, so one more time. Says probability sum is greater than 9. Let's use a little different color here than yellow then. Let's use the not bigger than either. All right. So one more time. First of all, we're looking for a sum greater than 9. How many of these 36 different combinations have a sum greater than 9? And that is 6 of them do. These 6. So 6 out of 36 have a sum greater than 9. It says greater than 9. Okay, so that wouldn't include 9. Right? Now it says how many of those 6 then have a white one that has the number 6 on it? Well, we could either say red or blue. Okay, but how many of them do? Then 3 of them do. Okay, So 3 out of those 6 then have a white 6. So that's 1/2. Now, since 1/6 is not equal to 1/2, then they're dependent because of that. So the probability of this happening is just 1/6 times 1/2. Or if you just look at it, how many did we circle twice out of the 36? 3 of them. And 3 out of 36 is, or a 12th. Okay. But one thing to notice is that these two numbers here are always going to be the same. Okay. The number in my numerator, my favorable outcomes for the first situation, is going to be my denominator, the total number of outcomes for my second situation. Okay? Look at another one. Let me pull this down. Okay. All right, so let's use, says the yellow cube shows an even number and the sum is 5. So we'll just say it's the blue one. We'll use blue. All right. So what's the probability the blue one has an even number? Blue has an even number. How many blue ones have an even number? Okay. Hopefully half of them, right? Okay, let's see. Column 2, the blues are all 2. Column 4, the blues are all 4. Column 6, the blues are all 6. So you've got 3, 6, or 8, 6, 12, 18 of them out of 36 have the blue with an even number, which is 1/2. So now we are focusing on these 18 combinations. Okay. So how many of those 18 then have a sum of 5? And if you can't see that well, then you could always look it up in your book. How many of them have a sum of 5? Let's see. Let's use green. Okay. So let's see. Here's 1, right? 2 and 3. None of the other ones add up to 5. Over here we have 1 and 4. Okay. And any of them with a 6 add up to 5? No. So this is 2 out of the 18, or 1/9. So this is dependent because 1/2 is not equal to 1/9. And then to find the probability, then we just multiply those numbers together, which is 1 out of 18, which makes sense because how many of them did I circle in green? 2 out of the 36. No, 2 out of the 36. Okay, the total ones. All right, is 1 out of 18. You would have to show this for why it's dependent, and then you multiply those two numbers together.
So like if this was not a multiple choice one, would it just be like 1/18 would be one of our choices, or is it going to be like?
Well, it would be dependent and 1/18 probably a choice, independent and 1/18 be a choice, or some other numbers than that. So what we're looking at is we're looking at this. Here's the key word right here, and. If it says this and that is going to happen, then you're using the conditional probability. which means that I have to show first that the first thing, what the probability of that is, then this numerator and this denominator are going to be the same. For saying, okay, this thing's happened first, so then how many times does this other situation happen out of those events then? Okay, so see if you can find, if they don't ask whether they're dependent or not, then you could do this. Find all of them that have a sum greater than 9, which is sum greater than 9. We already did this, right? Which is these. Oops, not there. Okay, there's all the ones that show a sum greater than 9. Okay. And how many of those with a sum greater than 9 is the red one greater than 4? Okay, and that would be 5 of them. So we've got these 5 then. Not those 5. Undo that. These 5 then show that the red one is greater than 5. So how many have I circled twice? 5 of them out of how many altogether? 36. So your final answer, the final probability answer is 5 out of 36. Because I had 6 out of 36, and then 5 out of those 6. All right, when I multiply those together, 1/6 times 5 out of 6, I get 5 out of 36. Okay?
Now, when it says red, the red and the
Mhm.
blue one, does
Yep.
that mean both numbers have to be greater than? Well,
No, just the red one. Yep.
has to be greater than.
Right. We don't care about the blue one. We're only focused on the red ones then, out of that group. All right. Okay? All right, now we can use a table to do conditional probability. And once again, this is very important that you look at when we talk about the word and, because we're going to do this type of thing whenever we're using the word and in that question. Okay? So here we have a table that shows domestic migration from 1995 to 2000. A person is selected at random. Find the probability. So does everybody know what immigrants are? Okay, what are immigrants? What do they do? What do immigrants do? Okay, they migrate here. And so emigrants with the E, what do those people do? Okay, they're born here? No, I think those people, okay, they leave. All right? So we got people coming and going. So it says, A says that an immigrant is from the West. Okay? So this means then I have to find this first. Okay? How many of them are immigrants? And then from that, how many of those people are from the West? Okay? So let's look at the immigrants. Oh, they don't give us the total, do they? Okay? So we need to find the total of immigrants first. So can somebody add those up for us? One, 656. Okay, so 11,656 immigrants. Okay, so how many of those people are from the West? Okay. Now this would be a problem where it would be okay to use a decimal for your answer, because more than likely the simplification of the fraction is just a big ugly fraction, right? So if we take 2,654 divided by, all right, and I change that to a fraction, right, really doesn't help me much, just divided by 2. So in this case, I would use 0.23. Okay. In that case, it's okay to use a decimal, all right, because it's a big fraction. Okay. Letter B, someone selected from the South region is an immigrant. Okay? So this means we're looking at, okay, the people from the South first, and how many of those people from the South are immigrants? So there are 8,285, right? People from the South, and how many of those are immigrants? Okay, so 5,042 out of 8,285. All right, and once again, we'll write that answer as a decimal then. Okay. But each of these cases, it's very specific. It says, okay, of the immigrants, how many of those are from the West? People from the South, how many of those are immigrants? Now, key word, like I said, is one we need to pay attention to, is this word right here. This says that someone selected is an immigrant and is from the Midwest. When they do that, when you end up using this word and, that means my final answer is out of everybody, okay? Total population. So which means we actually have to do some big calculations here. We need to find out how many people there are altogether. Well, we know the immigrants is 11,656. So then we need to add that number to all of the immigrants. 11,655. You did that already? All right. So altogether we have 23,331? 311. Okay. All right, that's the total people. Okay. So how many, and this is basically how you do this problem now then. How many of those total people are immigrants and Midwest? So here's what we do. Where's the intersection of immigrant and Midwest? What number? What? Okay. Where's the intersection of those two things, the column and the row? Right here, 2,951, right? Right there. Okay? So 2,951 people out of the total population are both immigrants and from the Midwest. When they use this word and, we're talking about the whole population. Just like in these problems over here. When we used and, all right, we're talking about all 36 things. When did both of those things happen with all 36 things?
So the total is going to be all the immigrants?
All the people, period. All right. How can we tell if things are independent or dependent then? All right. Well, we just found out one way. Okay? If those two parts don't equal to each other, then they're not. But the other thing is just if we change the probability, then they're dependent. Okay? So here's the easy way to do it. If we're talking about taking something where we pull something out of a basket or pull a card away, if I do replacement, it's independent because the probabilities haven't changed. If I don't replace it, okay, then they're dependent and the probabilities change. But in either situation, we're going to multiply. So here we have two cards are drawn from a deck of 52. Right? So that means there's 4 aces, 4 twos, 4 threes, 4 fours, 4 fives, 4 sixes, 4 jacks, 4 queens, 4 kings, and so on. Okay? 4 of each. Determine whether the events are independent or dependent and find the probability. So it says select 2 hearts when the first card is replaced. So I draw a card out. Right? What's the probability that the first card is a heart? Okay. 13 out of 52, right? Because there are 13 of each one, hearts, diamonds, clubs, or spades, which is actually 1/4. Okay? But we'll leave it as 13 out of 52 to start. Okay? Now, if I take that card and I put it back in the deck and shuffle it all up again, what's the probability I draw a heart out now? 13 out of 52 again. So I'm going to multiply them together. So that would be 1/16. Okay, 1/4 times 1/4. But this is independent. And it's independent because of it was replaced. Okay? The probability doesn't change. Letter B. Selecting 2 hearts when the first card is not replaced. So the probability the first one's a heart is 13 out of 52. But now I take that card and I set it down on the table. How many cards are in my deck now? 51, right? Okay. I took one out, I got 51 left. How many of those 51 now are hearts? 12 of them, because I took one heart is gone. I only have 12 hearts left. That's good. I need as many hearts as I can get. Okay. All right. So is this independent or dependent? All right. Because it was not replaced, it's dependent. Okay. But either way, then we are still going to multiply these together. So we get 1/4 times 12 over 51. How many times does 4 go into 12? 3. So this is 3 out of 51. What's that? Which is 1/17, right? Okay. And you got to remember to simplify your fractions. Okay, one more. A queen is drawn, not replaced, then a king is drawn. Independent or dependent? Am I putting the card back in or am I setting the card down on the side? Setting it aside because it says not replaced. So this means that it's dependent because it's not replaced. So what's the probability I get a queen the first draw? Okay. 4 out of 52. All right, I put that queen down. How many kings do I have now? 4. How many cards do I have? 51. Which is what? 663. Okay? So that's pretty small.